Hi, my name is Roberto Pacheco, and I present this paper about calibration of deep neural network with early exits in the edge. Deep neural network, also called DNN with early exits, consists of a regular DNN, but we insert these early exits, or also called side branch, into the middle layers. This approach is based on the idea that the features extracted by the first convolutional layers are sufficient to classify some samples early in this side branch. Therefore, this approach's goal is to accelerate inference time classifying some samples early in this exit. Let's see how works an inference in this kind of DNN. First, the image is processed by the first layer, V1, then it's processed by the first side branch, B1, generating an output denoted by Z1. Finally, we can compute its confidence prediction and compare if this confidence value is greater than a confidence threshold, denoted by p-tar. If so, the sample can be classified already in the side branch. Otherwise, the image must be processed by the next layers, such as V2, and so on and so on. In this work, we use an IEEE, a traditional benchmark DNN used in image classification problems. Then we insert a side branch after the first layer and we trained using image from CFAR10 dataset. For a DNN to be reliable, its confidence should be related to the probability of classifying correctly. Moreover, when DNN confidence is equal to its accuracy, we say that DNN is calibrated. However, Core in his work demonstrates that the confidence provided by the traditional DNN with no side branch are no more related to the probability of classifying correctly. So we say the DNN is miscalibrated. Also, Core has demonstrated that applying a simple post-processing calibration method called temperature scaling can provide a new confidence that is more related to the probability of classifying correctly. Consequently, this new confidence is more related to the accuracy. This paper evaluates the impact of the calibration method, temperature scaling, in DNNs with early exits using adaptive offloading scenario. Let's understand what is this scenario. In this scenario, we place one part of the DNN with all side branches on the edge side. Then, after this side branch, all layers are placed in the cloud. In this scenario, when the confidence provided by the side branch can't classify a given sample with high confidence, the edge device sends the output feature to the cloud. Thus, our scenario enables offloading as a function of data's complexity. Consequently, easier samples are classified on the edge side, while the harder examples are classified in the cloud. In this sense, when we increase the confidence threshold p-tar, fewer samples can achieve this requirement. Consequently, more samples must send to the cloud to be classified. Our goal is to demonstrate that miscalibrated side branch can overestimate its confidence prediction, consequently may take bad offloading decisions affecting the reliability of these decisions. To this end, first we measure the offloading probability and compare using uncalibrated and a calibrated DNN. In this sense, we count the number of samples classified early in the edge side, thus on the edge device, using no calibration method. Then we repeat the same experiment applying a temperature scaling method. Our first result shows the probability of classifying on the edge device on the y-axis and the confidence threshold p-tar values on the x-axis. We compare the results using calibrated side branch and a conventional side branch, which means an uncalibrated DNN. At first sight, we can note that for any p-tar configuration, the probability of classifying in the edge using calibration is less than conventional one. This result indicates that conventional DNN overestimates its confidence prediction, achieving more often PITAR requirements, consequently classifying more samples locally in the edge device. Then, for the same experiment, we compute the accuracy on device with no calibration method and using the calibration method temperature scaling. The result shows the accuracy on device in y-axis, which we compute accuracy considering only samples classified on the device, and PITAR in x-axis. We can notice that for any PITAR value, the calibrated DNN outperforms the conventional one. It indicates that the calibration method improves the ability to select what sample should be classified early on the edge side and what sample should be sent to the cloud. Comparing the results of probabilities of classifying on the device and the accuracy on the device, we can see that conventional DNA also classifies more samples early. However, this conventional DNA also classifies more samples incorrectly. This result shows that conventional DNA classifies more samples locally in the edge side than it should. Now, we evaluate accuracy total, which we compute considering samples classified in the edge side and in the cloud side. Again, calibrated DNN achieves a higher accuracy than conventional one. This confirms our conclusion that conventional DNN classifies more samples locally in the edge side than it should. At this point, we show that conventional DNA is overconfident about its inference. Moreover, we show that conventional DNA classifies more samples in the sidebrain than it should. Then we show that calibrated DNA is more capable to select what samples should be classified in the edge side and what samples should be classified in the cloud. Our next experiment measures the reliability of an uncalibrated and a calibrated DNA to meet an accuracy requirement. To this end, we define an event called outage. An outage occurs when the edge's accuracy can't meet the accuracy requirement, so the edge's accuracy is less than the confidence threshold, PITAR. For this experiment, we insert a batch with 512 images. Then we compute the edge's accuracy and verify if this value is less than the confidence threshold, PITAR. If so, an outage happens. This experiment allows us to compute the inverse outage probability. This result shows inference outage probability in y-axis and the confidence threshold PITAR in x-axis. First of all, we can see calibrated DNN remains 0 for more PITAR values when comparing with conventional DNN. This result shows that calibrated DNN is more likely to meet the accuracy requirement. Consequently, for a calibrated DNN, PITAR works as a Couto estimator of its accuracy because PITAR value acts as a lower bound to its accuracy. However, many computer vision applications, such as smart car, demand low latency. Consequently, this application must achieve not only accuracy requirements, but also must achieve the latency requirement. At this moment, we analyze how the calibration impacts to meet the latency and accuracy requirements. To this end, we define an event called missed deadline that happens when the DNN can't meet latency or accuracy requirements. In this experiment, we insert again a batch with 512 images, then we compute inference time as the sum of the edge processing time, network delay, plus cloud processing time. Regarding edge processing time, we estimate the processing delay on edge device based on the values reported in this paper in literature. This paper measures the processing delay required by each layer of an IEEE using an Intel i7 CPU. Then we also account for the network delay, which is occurred when sent the output data from the edge device to the cloud. The network delay is given by the output data size that sent to the cloud divided by the average uplink rate. We evaluate the output data size as the size of the data structure in PyTorch, and we use this average uplink rate derivative from a Wi-Fi scenario from this Infocom paper. Finally, regarding cloud processing time, we use the computational resources from Google Colab platform. After processing a batch, we can compute the edge accuracy and the inference time, so we can verify if this accuracy and this inference time achieve the requirements. If so, a missed deadline occurs. In this paper, we use the parameter beta as the accuracy requirement because we can show the relationship between confidence threshold and the accuracy. In this case, we should avoid a missed deadline. Consequently, less missed deadline is better. This plot shows for a fixed beta of 0.75 that missed deadline probability in y-axis and the latency requirement denoted by theta in x-axis. Oddly, we can notice that the conventional DNN artificially outperforms the calibrated DNN. Let's see the reasons why this result is artificial. First, let's remember missed deadline occurs when the accuracy total is less than a beta requirement or the inference time is greater than a latency requirement. Both requirements are defined by the application. As we have seen before, for beta of 0.75, both DNNs achieve higher accuracy than beta value. Consequently, missed deadline occurs only when the inference time is greater than a latency requirement. Conventional DNN wins because classify more samples in the edge device, reducing the inference time. However, when we evaluate more realistic scenarios with more severe accuracy requirements, such as 0.85, we can see that calibrated DNN outperforms the conventional one because this cannot achieve accuracy requirements. As we have already seen before, conventional DNN does not achieve the accuracy requirements. This result shows the importance of calibrating DNN for different latency and accuracy requirements. Our conclusion is that this paper provides evidence that miscalibrated DNN with early exits provides unreliable offloading decisions. We demonstrate that this problem can be mitigated by applying a simple calibration method such as temperature scaling. We introduce the inference outage probability as a metric of reliability for inference on the device. We also introduce missed deadline probability to quantify end-to-end performance for early exits DNN to meet an accuracy or a latency requirement. As future work, we intend to analyze how missed deadline probability affects the quality of experience for different DNN applications, and we intend to evaluate the DNN performance for other requirements, such as energy consumption. Thank you very much.